In this video, we're going to talk about exponents and exponential functions. So let's do a brief review. If we have a number raised to a power, we call this number the base, and we call this power the exponent. Now, if this number is a non-negative integer, so if you have something like 3 squared, then this is just 3 times 3. So this number right here tells you the number of times you're going to multiply that number with itself. So here you're multiplying 2 times. If you have something like 4 to the 5th, this is 4 times 4 times 4 times 4 times 4. So you would multiply all of these numbers out in your calculator, and that would give you your answer. Let's do some quick examples. So 2 to the 4th, that is equal to 2 times 2 times 2 times 2. Well, 2 times 2 is 4. This is also 4. So 4 times 4 is 16. So 2 to the 4th is 16. 3 squared is 3 times 3, which is equal to 9. You can see I have 2 of them here. Now, something I see students do, they'll forget that this is multiplying 3 by itself. They'll just say 3 times 2 and say it's 6. This is not multiplication. It's taking a number and raising it to a power. So you're multiplying this by itself for a total of 2 times. Now, if we have a negative in the exponent, how you want to deal with that is you want to take whatever you see and push it in the denominator. So this is going to be equal to 1 over 4 squared. So a negative becomes a positive when you push the whole thing to the denominator. So this will be 1 over 4 times 4, just like regular here, which is 1 over 16. 5 to the negative 3 is 1 over 5 cubed, which is 1 over 5 times 5 times 5. And if you multiply all that out, you'll get 125. So now we've seen powers that are positive integers like this, and also negative integers. Now let's deal with things that are fractions, like this 9 to the 1/2. So this is the same thing as the square root of 9. So if you have something like, let's say, just some number to the 1 over m, then you're taking the nth root of that number. So we know what the square root of 9 is. We're looking for one number that when you multiply it by itself for a total of 2 times, you get 9, and that happens to be 3. So it's 3 because 3 times 3 is equal to 9. So if I multiply it twice, I get 9. Another way you can think of this is you could say 9 to the 1/2 is equal to, well, this 9 is the same thing as 3 squared. And this 2, when we have, and I'll go back over this property in a minute, when you have a 2 and a 1/2, you can multiply them together to get 1. And so this is just 3. So you can think of it as a square root of 9, which is 3. Or, like I said, you could change this 9 to 3 squared and then multiply these two. 81 to the 1/4 is the 4th root of 81. And what we're looking for is a number that when we multiply it by itself for a total of 4 times, we get 81. And that number happens to be 3, just like the last one, because 3 times 3 times 3 times 3, well, this is 9 times 9, which is 81. Again, you could also write this as 81 to the 1/4 is 3 to the 4th to get rid of that 1/4. How about 100 to the negative 1/2? Well, just like I mentioned before, if you have negatives in the power, you can push it to the denominator. So this will become 1 over 100 to the 1/2, which is just 1 over the square root of 100, which is 1 over 10. Before we go to the next one, what if we have something like, how about I put 25 in the denominator? So 1 over 25 to the negative 1/2, like this. So when I had this negative 1/2, I moved everything to the denominator. The same thing happens if it's in the denominator. So if you have this negative, you can move it up to the numerator. And so this would just be 5 because this is square root of 25. So negatives, you can make them positive by pushing them up or pushing them down depending on where that negative is. So if you have a negative in the denominator, push it up. So this is the same thing as 25 to the 1/2 over 1, but you get 5. Okay, now we're going to deal with taking a number and raising it to not an integer, this you can write as a fraction, but like if you have a decimal or an irrational number. Now this stuff you can actually just plug into your calculator, and that's what I'm going to do here. So I'm going to share my screen of a calculator, and what I'm going to do is I'm going to plug this into my calculator, which is 2 to the, so I'm going to hit Shift and the number 6, and you're going to go up and you put 3.5 into that. And I'm using Desmos.com, by the way. So 2 to the 3.5 is about 11.313, and that's what I'm going to write down, 11.314. So let me share, Zoom share. Give me just a second. So we're going to put 11.314. I also want to show you how to do it on a graphing calculator, just so that you know where the buttons are, like if you have a handheld graphing calculator. So I'm sharing my screen again, and I just Googled a graphing calculator here. And you can see on this side, I have a bunch of buttons. So if you want to do 2 raised to this 3.5, you would just hit this number 2 here. And then you would look for the caret key, which is right here. So you push that caret key and then put 3.5 and then hit enter. And then you would get the same answer that I got. So let's go back. Let's do 6 to the square root 7. So write that down. Now let's go to our graphing calculator. So to put it into this one, you would hit 6, up, this key right here. And then you want that square root sign. You see how it's in yellow? So you do second, and then hit this button, and you get the square root, and then put 7 there, and then close that. I think they give you parentheses, so close that, and then hit enter. But I'm going to switch over to this one, and I'm just going to put, I think it was 6 to the, I'm going to type SQRT, and that'll give me the square root. When you have Desmos like this, you can just type SQRT and hit 7. But also I think you can, they have some stuff over here where you can type in, maybe it's down here. Yeah, so you can put a square root right there. Just make sure you're in the exponent. So it looks like it's 114.5. So let's round it to that, 114.5. So let's go back. So this is about 114.5. This one was an about sign too. Let's move on. Let's talk about some properties of exponents. We've already seen some of these, but we're going to use these later, so we definitely need to review all of them. So if you have a number raised to a power, and you're multiplying it by the same number, but it might be a different power here, all you have to do is add these two powers together. Maybe I can give you a quick example. So if you have 2 cubed times 2 to the 5th, this is going to be 2 to the 8th. Now this number has to be the same. So if you had 2 cubed and 3 to the 5th, then you couldn't combine them like this. These numbers have to be the same. These can be different, the powers, but the bases have to be the same. Over here, I have a to the m raised to the power n. This is equal to a to the m times n. And we've already done this a little bit because I made like this 81 to the 1/4. I said that 81 was the same thing as 3 to the 4th. And then I have this 1/4 here, and then I multiplied these two numbers. That's what I was doing here because I knew this property. So if you're not familiar with this property or you forgot it, that's okay. Let's give another example of this. So let's say we have 5 to the 7th, then to the 3 here. So this is taking 5 to the 7th, and we're multiplying it 3 times. And then 7 plus 7 plus 7, which is this property here, gives us 21. And that's why we can just do 7 times 3. This is 5 to the 21. Okay, let's move to the next couple of them. So here I have a times b. So these are two different bases, but they're both raised to this power m. Well, this is going to be the same thing as a to the m times b to the m. So for example, if you have 2 times 3 to the 9, this is equal to 2 to the 9th times 3 to the 9th. Can't combine these any further. So you would leave it like this, or you could say, if you could multiply these together, you could say this is 6 to the 9th. Okay. A to the power 0. So anything to the power 0 is just going to be 1 as long as a is not equal to 0. We'll have a problem. We can't take 0 to the power 0. But any other number is fine. So something like, let's say 12 to the power 0, that is 1. And if you do like -3 to the power 0, that's going to be 1. Also, 1 to the power 0 is equal to 1. But 0 to the power 0 is undefined. So that's the only number you have to take out. Let's look at this a to the -m. We already discussed this one. I don't think we need much practice with this, but this is equal to 1 over a to the m. And also I mentioned that a to the -m, if it's in the denominator, this is a to the m. And then finally, I have 1 raised to any number. 1 raised to any number is just going to be 1. And you can think of it like this. If I take 1 and cube it, well, this is 1 times 1 times 1, which is just going to be 1. And if you put it to some negative number like -10, well, this is 1 over 1 to the 10th, and then you have 1 multiplied 10 times, so you'll still get 1 over 1, which is 1. So any number, including 0 here, you'll get 1. Right, now we're ready to talk about exponential functions. So an exponential function is a function of the following form. F of x is equal to c times a raised to a power x, where a is greater than 0, so it's a positive real number, but a is not equal to 0. Sorry, a is not equal to 1, and c is not equal to 0. So we're going to put numbers like 2 here, or 3, something like that, or even like a half, and we're going to raise it to a power. And this, you can put anything you want here. This is any kind of constant, just not 0, because if you multiply this by 0, the whole thing's 0. So this is not going to be an exponential function. And you don't want this number to be 1 because, as we saw a minute ago, when we raise 1 to a power, we just get 1. So we're not going to get an exponential function there. So again, the exponential function takes this shape where a has to be greater than 0, so it's positive, but also a is not equal to 1, and the c, we don't want it to be 0. So that's the type of functions we're going to investigate in the next few minutes. So if we have an exponential function, what does this graph look like? Let's start with this function here. F of x is equal to 2 to the x. So notice that this number, which we're letting it be a, so remember that we said an exponential function takes this shape. So we're just letting c be 1 here, and a is the number 2, so it's definitely greater than 0, and it's not equal to 1, and it's raised to some power. Now notice that this is not equal to x squared, okay? These are not the same. Just keep that in mind. In fact, you can plug some numbers in to show that they're not the same. Like if I put a 3 here, for this one, 3 squared is equal to 9. But if I put a 3 here, 2 cubed, that's going to be equal to 8. So these are not the same thing. So these are going to be functions we haven't seen before. So if we want to graph something and we have no idea of what the graph looks like, the first thing you want to do is you want to just plot some points. So we're going to plug in some x values and see what we get when we plug them into the function. And then this will be your x, this will be your y, and you can just plot the point. So let's start with something easy. Let's plug in 0. Well, then we get 2 to the 0, which we said that this is going to be equal to 1. So let's plot a point at 0, 1. Now let's put in another x. So if I plug in 1, I get 2 to the 1, which is just 2. So I'm going to have the point 1, 2. Let's move that over a little bit. Now let's try something else. Let's plug in 2. So 2 squared is going to be 4. So I'm going to have the point 2, 4. And then if you plug in 3, you'd have 3, well, 2 cubed. In fact, let me make a little line here, make it a little bit longer. If I plug in 3, I have 2 cubed, which is 8. So now the next point is going to be way up here. So let me erase this and maybe extend this a little bit. So this is 1, 2, 3, 4, 5, 6. I think I went too far with this one. Okay, so we have, when we plugged in 1, we got 2. And then when we plugged in 2, we got 4. And then when we plugged in 3, we get 5, 6, 7, 8. And then if you plug in 4, you're going to get 2 to the 4th, which is 16, which is going to be way up here somewhere. So you can see that the graph is going to look something like this, at least on this side. Now, we can also plug in negative values for x. Let me zoom out a little bit. So let's try to plug in something like -1 in for x. If I plug in -1, I get 2 to the -1, which is 1 over 2 to the first power of 2. So we have the point -1, 1/2. So let me zoom in right here. So -1, well, here's 1, so half is, we zoom in even further, it's halfway, right? And then if I plug in, let's say, -2 into my function, I get 2 to the -2, which is 1 over 2 squared, which is 1 over 4. And 1/4 is smaller than 1/2. So we're going to have a point that's closer to 0 here. And the bigger the number, but negative, the closer you're going to get to 0. So if you keep doing this, what you're going to see is you're going to get, your line is going to get closer and closer to the line y is equal to 0. So in other words, you have an asymptote. This line y is equal to 0 is a horizontal asymptote. Because as x approaches negative infinity, this way, your function, f of x, it approaches 0. You can see that we're getting closer and closer to this value y is equal to 0. But as x goes to positive infinity, so as we go out this way, you can see that our y's are going up towards infinity. And I'm sure you've heard about exponential growth before, particularly with population growth. You can see that as x gets a little bit bigger, the y values they start to really differ. Because like right here, when x was 0, and then when you go to 1, this difference here from this point to this one is just 1 unit upwards. But then when you went from 1 to 2, you went up 2 units upwards. And then when you went from 2 to 3, then you went up 1, 2, 3, 4 units upwards. And you can see every unit you go out, the distance between your y values is getting bigger. Okay, so some other things to notice about this graph. Let's erase this chart so I have some room here. Okay, so some things to notice. First thing is we can talk about the domain and the range. So what's the domain here? Well, notice that I could plug actually anything I wanted to in here. I plugged in integers like 1 and 2, but I could plug in 1/2 and 3/2 and things like that, or 1.2222 or something like that. So the domain, and from the picture, it's negative infinity to infinity. Because you're going from left to right, you can see that you go out to negative infinity and also to positive infinity. As for the range, remember range is how far up and down you go. This graph obviously goes up forever, so it goes towards infinity. But when we go towards 0, we actually don't hit 0 because this is an asymptote. So the range is from 0 to infinity. So we have a horizontal asymptote at y is equal to 0. And notice that we have a y-intercept at 0, 1, because when we plugged in 0 for x, we got 1. But there are no x-intercepts. We don't ever cross this x-axis here. Something else we should notice about this graph is that the graph is an increasing graph. So the graph is increasing on the interval negative infinity to infinity. So out from negative infinity all the way towards infinity, this graph is going a little bit upwards and towards positive. So right here, although it looks almost straight, if you were to zoom in this graph, remember that the further you went out, the closer and closer you got to 0. So if you're going in this direction, you're going upwards, and then right here, you're going upwards really quickly. So this is an increasing graph, and also notice that is a one-to-one function. So the function is 1-to-1. And how do we know that? Because it passes the horizontal line test. If I drew a horizontal line anywhere, I would just hit this graph 1 time or 0 times down here, but I don't hit it more than once. And since it's 1-to-1, that tells us it has an inverse. So this function is invertible. We can find an inverse function for it, and we'll talk about that in a couple of sections later. Okay, so notice that this number 2, it is greater than 0, but it's also greater than 1. So this number here, 2, is greater than 1. The reason I'm bringing that up is because I want to focus on all exponential functions whose number, this base here, is greater than 1. So properties of the function f of x, which is equal to a to the power x, where a is greater than 1. So what are some properties? It turns out, let's look back at this graph. If you put any number here greater than 1, you're going to get the same looking graph. Why is that? So let's try a different number here. I'm going to erase this graph. And let's just give it a whirl and see what we get. And just, I guess we can ignore some of this right now. Okay. All right, let's say we put the number 10 here. So that number is bigger than 1, is actually bigger than 2, and you could choose something like 1.5 if you want to. If we were to plot some points, we would do the same thing, right? So we would say, first off, if we plug in 0, what do we get? We get 1, because 10 to the 0 is 1, so we'll get a point right here. So we go through the point 0, 1. Now if I plug in the point, if I plug in x is equal to 1, I'll get 10, which is way up here somewhere. And then if I plug in 2, I'll get 10 squared, which is 100, which is even further up here. It's way up there. But you're going to get a graph that goes up like this. So maybe move it over here somewhere. But this is the idea of what the graph is going to look like. So you're going to go up really, really high. And then if you start plugging in negatives, like if you plugged in -1, you're going to get 1 over 10, because this, you'll move it to the denominator, so you're going to get a value that's really close to 0. But if you put a -2, you're going to get 1 over 100, so you're going to keep getting closer and closer to 0. But let me try to draw this a little bit better. Like that. So it turns out that this graph looks a lot like the graph I drew just a minute ago. And all of the graphs where this number is greater than 1 is going to look like this, the overall shape. Now it might be stretched or something, or kind of smushed down, but the overall shape will look like this. So the domain and the range are going to be the same. You're still going to have the same horizontal asymptote, and your y-intercept is going to be the same. You're not going to have any x-intercepts. The function is 1-to-1, and it's invertible. So everything we had before, you're going to have with this type of function. So properties of this function, where a is greater than 1, let's write some things down. You're going to have no x-intercepts. You're going to have a y-intercept. And that y-intercept is always going to be 0, 1. Some other points on the graph that will help you draw the graph will be, you can plug in 1, you'll get a. So if this was a 10, if we plugged in 1, we got 10. If it's a 5, you plug in 1, you get 5. Also, if you plug in -1, you'll get 1 over a. The function is 1-to-1. And increasing. And you have a horizontal asymptote at y is equal to 0. Also, the domain and the range. The domain is all real numbers, and the range is anything from 0 to infinity. So that's always true when this number is greater than 1. Now, when we defined exponential functions, we said that a is anything that's a positive number, but not equal to 1, right? So we can also talk about things that are between 0 and 1. So that's the next step. So we've already done this. I'm going to move on. Let's graph this function. So now I'm focusing on the base being something between 0 and 1. So I have a half. Well, I'm going to do the same thing I did before. I'm going to plot some points. So I'm going to choose an x, and I'm going to figure out what I get when I plug it in the function. So plug in 0. Well, 1/2 to the power 0 is 1. So we're going to get that point again, this point 0, 1. But notice what happens if I plug in 1. This time I get 1/2 to the 1, which is 1/2. And if I plug in 2, I get 1/2 squared. So if I double this, I get 1/4. So as I get bigger in this direction, I'm getting closer to 0. But if I plug in negatives, like a -1, so 1/2 to the negative 1. Okay, this might be a little confusing, but push this to the denominator. This is 1 over 1/2, which is 2. So then you're going to have a point at 1, 2. And if you plug in negative 2, you get 1/2 to the negative 2, which is this thing to the negative 2, which is 1 over 1 over 4, so you get 4. 2, 3, 4. So this graph is going to look like this. And compare it to the other graph I drew. What's the difference here? Well, the difference is it's been flipped with respect to the y-axis, x is equal to 0. We flipped it, it's the mirror image. So let's write some information about this down. So one thing to notice is we again have no x-intercepts. We have a one-to-one function. This time the function is decreasing. We have a y-intercept at the same spot, 0, 1. Our domain is still negative infinity to infinity. And our range is still 0 to infinity because it's just the mirror image. So that doesn't change the domain here or the range. Anything else we discussed before? Let me just look back over. And we have a horizontal asymptote at y is equal to 0. Okay, so I want to mention that if I change this number to anything between 0 and 1, the graph is going to look very similar. If I put a 1 over 3 or a 1 over 2,000 or something like that, I would still, if I raise it to the power 0, I would go through this point. If I put a negative number in there, then this side would go up towards infinity. And if I put something like a positive number, the bigger I get, the smaller this value will get, and it'll get closer and closer to 0. So all of the graphs will look like this. So let's write that down. Some properties of the function f of x is equal to a to the x, where a is between 0 and 1. So here are our properties. They're very similar. We're going to have no x-intercepts. We're going to have a y-intercept of 0, 1. We're going to have a horizontal asymptote at y is equal to 0. We're going to have a decreasing function that's 1 to 1. The domain and the range are the same as before. And then we're going to have 3 important points that will help us graph this function. The points are, let me write it like this, points on the graph are 0, 1. If we plug in 1, we get a. And if we plug in negative 1, we get 1 over a, just like we expected. But this number is actually 1 over something. So this a is going to be that flipped. And this negative 1 over a is going to be that flipped as well. So sorry, this one's going to be flipped, and this one is just that 1 over whatever that number is. Okay, before we move on, we actually don't need to memorize all of this stuff down here, because I'm going to show you a quick little trick. I mentioned it before. All you really need to know is the properties of this a to the x when a is greater than 1. And the reason for that is, and I'm going to put it right here, 1/2 to the x is equal to 2 to the negative 1 to the x. Because 1/2 is the same thing as 2 to the negative 1, right? So since it's the same, then you can multiply these two together and you get 2 to the negative x. So if y is equal to this, y is equal to 2 to the negative x. And then I have a negative inside here. And you can think of the parent function. So we have this function that we drew before, which was 2 to the x. You can think of that as a parent function. And then plugging in a negative inside that function, we know that corresponds to a flip about the y-axis. and then you get this function here, 2 to the negative x, which is what we have. So all we really need to know is how to graph something like this, 2 to the x, where this number here is greater than 1. Move on, and I'm not going to graph this one because we discussed, we know what it's going to look like. It's going to go down like the other graph before. So I want to graph, just do a few graphs involving transformations of functions. Here I have the function f of x is equal to 2 to the negative x minus 3. How would we graph this? Well, we start with a parent function. That parent function, you can call it f1 of x. You can call it a different letter, whatever you want to call it, but you need to notice that this looks like 2 to the x. And we know 3 points that this graph goes through, 0, 1, 1 comma this number, which is 2, and then also 0, 1 over that number. So this graph is going to look like this. So you're going to say this is 2 to the x. And then I'm going to put right here these numbers. So this is 1, 2. This one is 0, 1. And then this point right here is negative 1, 1/2. And then to graph this function, well, we ask ourselves, what do we need to do to this function to get this one? One thing we could do is we could move it down 3. So we define a new function, f2 of x, which is f1 of x, but moved down 3 units. That will give us 2 to the x minus 3. So we just take this graph and move all those points that we drew down 3 units. So this one will go down 1, 2, 3 to here. This is 1, negative 1. Let me erase this graph now and get rid of this point. This 0 to the 1, we want to move that down 3. So 1, 2, 3, move it here. And then this one is going to be moved down 3 units right here. And since this was negative 1, 1/2, if we move it down 3, this is 1/2 minus 3, which is 1/2 minus 6 over 2, which is negative 5 over 2. Just so I know what that point is. And then I'm going to just draw this graph that looks very similar. And notice that my asymptote also moved down 3 units. So the asymptote was originally y is equal to 0, but now it's going to be y is equal to negative 3. And then to finish this graph up, we've got to get this negative x involved. So then we define our new function, f3 of x, which is taking this function here and plugging in a negative x wherever I see an x. And that will give me the function that I want, which is this f of x. So that means when I graph this f3 of x, this will actually be the graph f of x. So when we're plugging in a negative, that means we flip about the y-axis. So if we flip about this y-axis here, this point will stay the same. This point will go over here, and then this point will go down here. So this 1, negative 1 will become 1, 1. Negative 1, negative 1. We're changing this x value. And then this point, negative 1, negative 3/2 will become 1, negative 3/2. And then we can finish this drawing up by just connecting these dots and moving upwards like that. So that's the idea behind graphing this. You're going to see this new number in the homework and in your textbook. And this number is called the number E. I'm going to show you where it is on if you have a graphing calculator, but we also want to discuss what it is. So let's think about 1 plus 1 over x raised to the power x. This number E is this expression when x goes to infinity. So if we start plugging in numbers, let's see what happens. If x is equal to 2, if I plug it into here, I get 1 plus 1 over 2 squared. So this is 3 over 2 squared, which is 9 over 4 if I multiply this by itself. And if you plug that in the calculator, 9 over 4 is about 2.25. Now let's make this x bigger. Let's say x is equal to 3. So if I plug that into this expression, I get 1 plus 1 over 3 cubed. Wherever I see an x, I'm plugging in 3. So this is now, this is 3 over 3, so this is 4 over 3 cubed, which is 4 times 4 times 4 over 3 times 3 times 3. This 3 is sent to everything inside. So that's, I'm going to put that in the calculator real quick. So 4 times 4 times 4 is 64. And then if you plug in 3 times 3 times 3, that's 27. And if you take 64 and divide it by 27, you get 2.37. And you can see that this number is close to this one, but it's a little bit bigger, right? So let's plug in something really big, like 100. So let's plug in 1, let me write it here. X is equal to 100. If you plug that in, you get 1 plus 1 over 100 raised to the 100. I'm going to share my screen here. So if I erase this, 1 plus 1 over 100 raised to the 100, I get 2.7 something. And you can see it's still close to 3, but it's 2.7. So it's bigger than the last value. Let me share back the other screen. This is about 2.7. The other one was 2.37. This is now 2.7. So it looks like we're getting close to 3. And so that's what the number E is. E is equal to the limit as x approaches infinity, 1 plus 1 over x raised to the x. So if you put a really, really, really big number in here, like a million and a raised to the million, the bigger you get, just keep putting more bigger numbers in there, you're going to see that you're getting close to a particular value. And let me show you what that number is. So the number E, in fact, all you have to do in Desmos is just type the letter E, and it's 2.71828. So that's about what the number is. It's an irrational number. It goes on forever, but you can say it's about 2.718. And notice, let's plug in something really big. So this 1 plus, let's do 1 over a million raised to the million. So you can see that this number is a little bit smaller than this one, but the bigger, so let's put another 0 in there, and here. You can see that we're getting very close to this number. You can keep adding zeros. You can see we're getting closer and closer to the number. So this is the number E. Also, if you look at your graphing calculator, right here, you can find the number E. You see it's right here where the M is. If you hit second, this yellow key, and then this key here where you see the E, that will give you the value. I think also you can do the second and hit this ln key. You see e to the x, it'll say e to the power x, and you can just plug in 1 for that power, and then it'll give you, if you hit enter, it'll give you what you want, the 2.71 something. Okay, so let's go back to our notes. So something you'll be asked to do in the homework is to graph exponentials involving this 2.71 number here. So we want to graph the function e, negative e, I'll write it here, f of x is equal to negative e x minus 3. And you might be wondering, how do we graph such a thing? It's actually not bad at all, because this number, the number e, is about 2.718, which is greater than 1. So this is an exponential function where this number is greater than 1. So we have a function like this, a to the x, where this a is e. So it's going to look like that graph we talked about. It's going to just look like this. So let's graph this e to the x. We're going to start with that because you can see it's a transformation. So if we start with a parent function, let's say f1 of x is equal to e to the x. Well, this is going to go through 0, 1, because if we plug in 0, 2.718 to the power 0 is 1. It's also going to go through 1e. Well, e, if we plug in 1, we get e, and e is about 2.718. So we can just say here's 2, here's 3, so it's about right here. Somewhere bigger than 2.5. And then if we plug in -1, we get 1 over e, but you can put that in the calculator. So if you do 1 divided by e, it's about 0.36. That's what I have. I rounded, so about 0.36. It's definitely less than 1, so it's going to look like this. We know that the function looks something like that. This is f1 of x. And now how do I take this function and make it look like this one? Well, there's a few things I need to do. I need to put this -3 here. So I define a new function, f2 of x, and it's taking this function f1 of x and plugging in x minus 3. That will give me e to the x minus 3, because if I plug that in here, and because I have it inside the function, that means I shift the graph to the right 3 units. So this dot now goes 1, 2, 3 here, and this dot goes here. I'm going to erase that stuff. So we're going to have something like this now. And this is the graph f2 of x. And if you want to label these 2 points, so this one was 0, 1, but now it's going to be 3, 1, because we moved it over 3 units. And this point was 1e, now it's going to be 4e. And then the next step is to take this function and put a negative on the outside. That means we need to define a new function where we take this one and just multiply it by a negative, which will give us what we want, the final answer. And when we multiply a function by a negative, we flip it upside down. So then all we have to do is take this number, which is 3, 1, this point, which is 3, 1, and make it 3, -1. And this one will be 4, -e. And so the function is going to look very similar. It's going to go down like that. It's just the mirror image. And this is the function f3 of x, but because it's exactly equal to this, this is the function f of x. So f3 of x is equal to f of x. And I could ask you questions like, what's the domain and the range? Well, now you can see that the domain is still all real numbers. The horizontal asymptote is still y is equal to 0, but the range has been flipped upside down. It's -infinity to 0.